So welcome back everybody to our final session for the European and UK lunch break, and maybe a different break for others. So it's a pleasure to introduce Tobias Eljasik-Swoboda from Fernuniversität Hagen, which is the distance university in Hagen for the UK participant. It's the Open University equivalent. And so when we discussed his invited talk, Tobias and I discovered that we were born in the same town in Germany called Wattenscheid. So it's good to have somebody from home here. And also Tobias just defended his PhD with the German degree of summa cum laude. You can't have nothing better. So in Germany, so very well done and congratulations. And I think your talk is about your PhD topic as well. So fantastic.
Well, it is, yeah.
So Tobias, stage is yours.
Great, thank you very much. Can everybody see my screen? Okay, great. So then I will now start my presentation. And yeah, well, welcome to my presentation about bootstrapping of explainable text categorization in emergent knowledge domains for example-based querying. As Ingo just said, the first part of this title is basically the title of my PhD thesis, but for today, I explore how this can be applied for example-based querying, and I'm very happy to talk about this topic. So you already heard my name, Tobias Eljasik-Swoboda, and well, let's get started. So we start with an agenda of what we will cover today and start with an introduction and motivation of why to prefer bootstrapping of explainable text categorization in emergent knowledge domains, in this case, for example-based querying. Follow this up with desk research results in the state of the art in this field, and come to an artifact design to overcome identified problem fields. This artifact has been experimentally evaluated, and I will share the results with you. And well, then we come to conclusions about this work. So let's dive right into the motivation and problem statement, because the fundamental problem is the digital information overload. In the era of the internet, we are constantly bombarded with a myriad of different information types that's available, and most of this stuff contains text in some form. One approach on handling this, at least everything that contains text, is the so-called text categorization. In text categorization, well, text is classified into content-based categories like these. On some applications, for instance, could be browsing-based information retrieval or faceted search. And there are two fundamental approaches of how to automate text categorization, as you may know. So the first one is to use rules and create a rule-based classifier and program them. The other one is to use machine learning. In its basics, machine learning, you have a learner, you get an input and an expected output, and the learner generates a so-called model. In this case, a model is an automatically generated algorithm that can then takes the input in order to perform the output. Here the output is, well, telling you what box to put the text into. And it sounds simple, but there are several problems upon the introduction of machine learning based text categorization. The first field is a high technical integration effort. The methods and frameworks are far from trivial, and you have to know how to use them, and not every programmer can do so. The second issue is the lack of appropriate learning resources. In this context, learning resources are the labeled input-output pairs, as well as other resources like dictionaries or ontologies, which is especially tricky for highly detailed domain knowledge. And well, the third issue is the explainability of categorization decision. The GDPR forces every algorithm in Europe that's impacting a European citizen to be explainable. So this is an issue with a black box machine learning model. And well, the last issue is semantic shift and emerging categories. Knowledge is constantly created, new boxes emerge where to put something, and old assignments might no longer be relevant. Therefore, the shifting of meaning and emergence of knowledge can be an issue for MLTC systems. So summary of the desk research we have performed. Overall, for this work, we have analyzed 267 different sources, and I have no time to go over them all. Therefore, I'll just give you the highlights of what we found. And the first fundamental is that MLTC always happens in phases. The first phase is the actual or zeroth phase, is the text extraction in itself, where the text is extracted from a document, be it an image via OCR, sound, or maybe even a longer document where individual sentences or paragraphs are extracted. Then follows a feature extraction in which it's transformed into numerical vectors, followed by a feature selection in which redundant numbers in this vector are removed. And this is followed up with a real machine learning task in the end. What we have also found that there is an abundant variety of feature extraction, selection, and machine learning approaches, reaching from artificial neural networks over statistic-based solutions over to solutions using high-dimensional geometry. Some highlights that work well and have subsequently used, we have already heard it today, TF-IDF, of course, models how relevant the term is for a specific document, and support vector machines are a machine learning classifier using high-dimensional geometry and creating decision boundaries and deciding if something belongs to one category or not by measuring if it's above or below the hyperplane. One can use a so-called kernel trick. You basically substitute the dot product with another equation, and what comes out are banded hyperplanes in this space, so you can create much more complex spaces in this feature space. And of course, the usual way of how to measure it, precision recall and F1 as the harmonic mean between them. And another interesting finding were the concept of microservices as themselves. Usually applications have been created in layers. So you have a user interface layer, an application layer, and a data storage layer. And microservices go another way. Here, the applications are split up by capabilities, and you have the individual layers all in this service, and you create the entire application by composing it out of individual microservices. Other findings are, of course, a whole world of word embeddings, where different words can get coordinates, and the offset between the coordinates encodes some kind of meaning. So what we see here is a gender and an age offset. Popular algorithms for this are skipgram, SIBO, and GLAV. Also, one has to form something that goes from an embedding to a document representation. One can, of course, do it with LSTM networks or something else that takes ordering into account. Other approaches are the paragraph to WEC approach, the word movers distance, or the basic additive model. And one important finding was Dice algorithm. Dice algorithm is highly interesting because it's an unsupervised classifier. One might wonder how that should work. Well, based on word embeddings, it takes the meaning of the individual class labels into account in order to create a classifier for it. Unfortunately, it so far has only been tested with tweets where it classified if somebody was twittering about having the flu or not. And also, there are the so-called transformer-based language models. So instances are BERT, GPT-2, or GPT-3. And these are very large-scale neural networks, and they create something quite similar to word embeddings, but the addresses of the individual terms are different depending on where the term occurred in the sentence. So the common example is I made a bank, and the other one is I made a bank deposit. And here the individual words have vastly different representations because they have different meanings depending on where they are in the sentences. And what you see here is a representation of the LIME algorithm. LIME stands for Local Interpretable Model Agnostic Explanations, and it's a black box post-hoc machine learning model explanation algorithm. Wow, what a long word. In German, you can put it all together to just one word. And what it basically does, it approximates the decision surface of a more complex system by slightly modifying the individual feature values to see where it stands. A very similar algorithm is a so-called Shapley additive explanations algorithm, or short SHAP. And it does something very similar, but it uses game theory to weigh how much the individual features impact the overall result. Both have a few drawbacks, namely that they have a lot of runtime requirements, and recent research has shown that one can build a classifier that fools these explanation algorithm and has a very problematic model, for instance, racist or sexist in place, but it can detect that it's being limed or chapped and generate results accordingly, so that it says, no, I'm not racist, I'm not sexist in this case. So some interesting work. So in summary of the stuff we assessed in the state of the art, nothing solves all the problem fields we mentioned before, but they are candidate technologies to create an artifact that overcomes these problem fields. So that's what we have done. What you see here is a component diagram of the Cloud Classifier Committee. It's a microservice-oriented application consisting out of different microservices. One is a committee microservice that can take other individual classifiers' results into account to generate its results. A machine learning-based text categorization microservice. The NTFC stands for No Target Function Classifier, so it's also an unsupervised classification algorithm, and the taxonomy extension system for emerging knowledge. They all can be directly interacted with by a user, or the user can interface with a command line interface, which can control all these things, making up this this microservice-oriented application. Based on this, for the domain of machine learning-based text categorization, a common information model has been created, and it importantly contains always an explanation for why was a result generated, and something that's implementing this interface always should provide such an explanation. What you see here is a trainer-athlete pattern. To the best of my knowledge, before this works, there was no pattern for machine learning-based text categorization in microservices. So the trainer-athlete pattern follows the common CQRS pattern for microservices and splits up the generation of models from the application of models into individual services, which are loosely coupled and communicate with the model interface where they exchange the model data that's being used. Based on this, a common information model has also been split up. So we have a classifier athlete and trainer model that can be used for the implementation of these kinds of services. Well, that's what we did. The machine learning-based text categorization classifier that is quite quickly applicable for a lot of stuff is based on TF-IDF and SVM. What you see here is a normalized TF-IDF equation. And what it basically does is it's doing a dimensional normalization for TF-IDF vectors, so they can be used as representation in a support vector machine algorithm. What's important here is that we limit the amount of terms and features that are taken into account with the variable. The default is 20. So we only take the top 20 TF-IDF terms per category from the training set into a controlled vocabulary, and everything other is ignored. We do this because we found out it's quite beneficial on one hand that a lot of noise is removed from the learning process, and then the comparatively simple SVM model in the background could create quite good results. So what you see here is a model that is used by the system, and well, it has vocabulary entries. So this was generated by the TF-IDF equation in the beginning. So we see what stuff should be taken into account and what not, and well, everything else about the SVMs for them to work. What's quite interesting here is that one can base explanation based on the selected features. Due to the fact that only a few features are taken into account, the occurrence of these features or keywords in individual text are strong indicators that these are the reason for the classification decision, because they differ between the individual categories. And therefore, a natural language explanation can be generated. The next one is a no target function classifier. It's an alternative to DICE algorithm. I also implemented DICE algorithm, but found that this one worked better. And what it basically does, it also works on word embeddings that have been previously generated. Then categories and the text are loaded into the microservice. And then there's basically a loop through the individual categories and their text representation to find the most closely related in the word embedding space. And this is basically an unsupervised classifier. It's parameterizable by selecting different word embeddings and different measures like the word mover's distance or the basic additive model and a cosine similarity. Explanations are also generated in a natural language, and they are based on semantic similarity between documents and category labels. And well, we evaluated all those microservices in different tasks. And the first task is argument stance recognition in the Recom Ratio project. What we do here is identifying for individual sentences if they are a pro argument or a contra argument. There are two different benchmarks with roughly the equal amount of documents or utterances. But what you see here is the ACAM benchmark has almost 800 different topics, while the UKP benchmark only has 8 different topics for which something can be pro or contra. We did article triage, so deciding from PubMed abstracts if they belong to a certain topic or not. News article classification using the Reuters data set, where we limit ourselves to the top 10 most relevant categories. And also what's quite interesting, we did this for German offensive language detection in the Germany challenge. It's quite interesting because all the other tasks were in English, and we just used the same tool and just applied it to a German task. And the last stuff we evaluated it with was intent recognition with or without any coded named entities. Intent recognition is what Siri or Alexa do, and basically what does the user want from me. And you can do it with additional information or not. Like if you have a library of song names and you know what the user playlists are, that's a lot of additional information that you can look up. And you can insert this in the workflow of the individual microservices to have this knowledge or don't have this knowledge, and can create comparisons. What did we evaluate? We evaluated our TF-IDF SVM classifier using the top 20 TF-IDF terms. And we evaluated the NTFC microservice, which also used DICE algorithms, so we can see which one performed better. We also evaluated a committee of both, and the most important result was that setup and application integration for those different tasks always took less than 75 minutes. And everybody who has created a classifier in the past knows, well, it takes longer, even if you're already familiar with this stuff beforehand. So what are the results of those experiments, you might ask? Well, I'm going to share them with you. So in the first task, we had this ACAM benchmark with almost 800 different topics and created a model using only the first 40 different topics that are available to identify, to tell pro from contra. And here we had an 85% micro average F1. But we found out the contra category was much better than the pro category. The tool off the bat does not know they are mutually exclusive. And well, then we took this model and applied it to the remaining 750 topics. And what we had here, okay, it dropped down to 57 F1, but we already knew, okay, this stuff is much better at detecting contra categories. Maybe we just add one line of code and only takes this decision into account for everything. And well, this boosted the effectiveness up to 71%. Just for comparison, the ACAM detecting stance in tweets challenge winner had 56% F1 for previously unseen topics. It's a different challenge. It's not, well, it's an apples and oranges comparison, but I want to illustrate that stance detection is not trivial. What we did then is we used the same on the UKP corpus, which only had the 8 different topics. Here, the micro average F1 dropped down to 46%. But again, we did the same trick of taking only the contra into account, and we achieved 58% micro average F1. What we then did is we created a model using UKP data and evaluated it with UKP data, and there we had 60% F1. Now switch from English to German, and we did the offensive language task, and here we had a 60% F1 off the bat, but again found, okay, the tool is better at identifying the other not offensive category over the offensive category. Therefore, we added this additional line of code, which boosted it to 70%. Just a few comparisons. In Starp et al., the guys who created the UKP benchmarks, they achieved 67% F1 with a highly fine-tuned systems for this task. Well, we were 60 with our added line of code. And for the Germany challenge, well, we did not participate because we learned about it shortly after it was concluded. But had we participated with the off the bat system of 60%, we would have been placed 42 or 52. And with the added one line of code, using the knowledge that we are better at detecting the other category, we would be at 70%, 7% below the winner with a highly fine-tuned system and, well, 20 seconds of all. For intent recognition without additional information, 64% F1 was achieved, but with additional information. So when we already know something is a song name and add it into the utterance for the classification, well, it was boosted up to 98%. Well, for the Reuters task, we had 77% F1, and for the article triage, 81 F1. Time flies, so just a quick overview of the results for the unsupervised categorization. Well, it worked best with highly literal category names. It worked poorly with abstract categories like argument, stance, or offensive language. One needs examples for that. The best distance measure was a word mover's distance, and the NTFC algorithm outperformed DICE algorithm. Word embeddings were also better from larger sources, and well, in committees for literal categories, it highly increased robustness and produced better result for underrepresented categories. Therefore, macro average effectiveness was growing. And for abstract categories, well, it mainly added noise to the system. So thinking about applying this for example-based querying, well, we think it's perfectly suited for this task because, well, this committee can classify an example document and the documents assigned to the same category are returned. What's good here is that we require little data or even no label sample data in the case of the NTFC microservice, and generate human readable explanation why those microservices classified the example to those categories which content is returned later on. Therefore, this concludes my talk today. I'm hoping I am not too much over time, and thank you very much.